So hello everyone, my name is Anne Cui from UT Austin, and today I'm presenting our results of maximized lateral inhibition in paired magnetic domain-wall racetracks for neuromorphic computing. So we're now in the era of big data and artificial intelligence. So in handling these data-centric tasks, it's becoming more and more important to decrease the energy budget related to computing. So neuromorphic computing is a paradigm inspired by the human brain, and it has a great potential for achieving truly low-power computing. So the artificial neuron is one of the basic components of a neuromorphic hardware. So here we're focusing on a spintronic neuron called a domain-wall magnetic tunnel junction neuron, and I'll refer it simply as a domain-wall neuron from now on. So the neural activity could be described by an integrated fire process. So a biological neuron can take the current input and gradually build up its main-brain potential. And once such potential goes over a certain threshold, the neuron can generate an action potential or a spike. So likewise, the domain-wall neuron can also capture such behavior. So first, in the integration phase, the domain wall in the racetrack is driven by spin or electrical currents towards the magnetic tunnel junction, or MTJ. And after it passes underneath it, the MTJ magnetoresistance will be switched low and an output current is generated at its terminal. So the neural activity is encoded in a domain wall velocity and position. So the neurons with a higher domain wall velocity will fire sooner and is therefore more active. So in addition to the integrate and fire function, there is another very important neuron function called lateral inhibition. So it refers to a process that an active neuron will prevent its less active neighbors from firing. So it is very important in the brain since it will result in a selective firing of the neural ensemble. And also in the research of artificial neural network, it can be used to implement various competitive learning algorithm. So in the domain wall neuron, the lateral inhibition means that the neuron with a larger domain wall velocity can impede the domain wall motion of its neighbor. So here is a schematic that shows the magnetic straight field interaction between a pair of domain wall neurons. So neuron N is active and neuron I is relatively inactive. So the neuron I domain wall will experience a straight field in -z coming from the up domain of the neuron N. So I will show later in this talk that this field is able to reduce the domain wall velocity of domain wall I, which is the inactive neuron, and therefore leads to lateral inhibition. So since the lateral inhibition of the domain wall neuron arises from the magnetostatic interaction of the neuron itself, it is intrinsic to the device. So there are no external circuitry required to implement such feature, and it will reduce the chip area and power consumption. So our goal is to maximize lateral inhibition by finding an optimal straight field strength. So to do so, we first simulate the domain wall motion in an isolated domain wall racetrack. So we keep the input current density unchanged and vary the externally applied vertical magnetic fields and simulates the corresponding domain wall velocity. So eventually we could obtain the velocity versus field relation as shown in this graph. So we can see that an external field of -9 or stat will most effectively reduces the domain wall velocity. So suppose a field is actually coming from the neighboring neuron. We can achieve such field by choosing the correct neuron spacing. So now we move on to simulate a pair of side-by-side neurons to determine the optimal neuron spacings to achieve maximum lateral inhibition. So likewise, we vary the neuron spacing and simulate the domain wall velocity both under inhibition or non-inhibition conditions. And then lateral inhibition could be calculated based on a reduction of domain wall velocities under inhibition condition. So in the end, we are able to achieve a 75% of domain wall velocity reduction or lateral inhibition at a 90 nanometer wire spacing. So we now take a closer look at the mechanism of domain wall neuron lateral inhibition. So it could be seen in a polar plot here that the domain wall velocity is directly related to its angle or orientation. So at 60 nanometer neuron spacing, the field strength is too strong, so domain wall is in the Walker breakdown regime. So as the domain wall precesses, its velocity will be averaged over all angles. However, when the spacing is larger, from 90 nanometer to 150 nanometer, the field is much weaker. So the domain wall is now below the Walker breakdown and has a fixed angle as it propagates. So specifically at a 90 nanometer neuron spacing, the domain wall has a minus 45 degrees angle, and this would correspond to a smallest domain wall velocity and therefore largest lateral inhibition. So we have just looked at the lateral inhibition in a pair of domain wall neurons, and now we move on to study an array of domain wall neuron, and we can see that the lateral inhibition is able to modulate the domain wall velocity distribution in the array. So as shown on the left, there are 1,000 domain wall neurons arranged in an array, and we should know that the spacings are alternating between S1 and S2, which are unequal. So this arrangement is intended to break the spatial symmetry of the two neighbors, both on the left and on the right. So this will prevent the stray field from canceling each other. So we use a inhibition model that is extracted from our micromagnetic simulation results and simulates the domain wall velocity distribution both with and without lateral inhibition. So we can see that when there is lateral inhibition, the overall domain wall velocity will be lower. So this means that if we have a certain time window for outputting the neuron spike signal, due to lateral inhibition, there will be a smaller portion of neuron that can fire. So this is potentially very useful for implementing the selective firing of the domain wall neuron array. So as a conclusion, we first maximize lateral inhibition by choosing an optimal lateral spacing and therefore the stray field magnitude. And then by simulating a domain wall neuron array, we have shown that lateral inhibition can modulate the domain wall velocity distribution, and it can be potentially used to implement competitive learning algorithms. And finally, we would like to acknowledge fundings from the NSF, the India National Laboratories, and the HPC resources from TAC of UT Austin. And thank you.